Welcome. In this video, we're going to be talking about what a nonlinear system is and how to solve a nonlinear system by graphing. So if you remember back to linear systems, we would talk about two lines and how they could either cross exactly once, how they could be parallel and never cross, or how they could actually be the same exact line and cross infinitely many number of times. But when we had two lines that cross, we would say that that point or that ordered pair where they crossed is the solution. So we're going to extend that idea in this section to say, well, what happens if, since we just spent a whole unit talking about quadratics, what if we had a quadratic and a line and that was our nonlinear system? So a nonlinear system is just a system in which at least one of the functions that we're talking about isn't linear, just one. So in this case, in this video, we're going to be focusing on what happens when we have a quadratic equation or a parabola and a linear equation or a line. So just like with two lines, there are three possible outcomes. It is possible that they have no solution because they never cross. It's possible that they have exactly one solution because they cross exactly once, or that they have two solutions because they cross twice. So what we're looking for is where these two functions intersect on the graph. So we're no longer talking about where a quadratic intersects with the x-axis. We're talking about where the quadratic intersects the line, or if the quadratic intersects the line. So the number of solutions again can either be 0, they never cross, 1, they cross at exactly one point, or 2, they cross exactly twice. So we're first going to look at some graphs and identify where they cross. So looking at number 1 down here, I'm going to darken this blue quadratic. And I'm going to darken the red function here. And we're looking for the 2 points at which these two functions cross each other. So not where they're crossing the axes, but where they're crossing each other. And that's happening here and here. So it's happening twice. So if we were just asked how many solutions are there? There are 2. And what are the 2 solutions? They are negative 1, 1. That's this point. And this point over here is 2, 4. So the two functions have 2 solutions, or 2 places that they intersect. They intersect at the point negative 1, 1 and the point 2, 4. I want you to look at number 2 and I want you to ask yourself first, how many times do they intersect? And where do they intersect? How many times do they intersect and where do they intersect? Well, looking at the green line and the blue parabola, they never cross. So there is no real solution because they never cross or they never intersect. Go ahead and do the same thing for number 3. Look at the blue parabola and the red line and identify how many times they cross first. How many times do they intersect? And that is 1. They intersect once, and that one time is right here. And then go ahead and identify what that solution is. And that solution is the ordered pair, negative 1, comma, negative 1. So that's identifying the solutions to a nonlinear system from a graph. You're just looking for the points where they cross. Again, it's possible that they cross never, that they cross once, or that they cross twice. Now let's look at what do we do if we are not given the graph for the nonlinear system. So if we aren't given the graph of a linear system, a nonlinear system, that's fine. We know how to graph. Let's just review briefly how exactly we graph. So we're going to start by graphing our line. You can, of course, graph your quadratic first, but hopefully graphing the line is going to be a little bit more efficient. We know that in slope-intercept form, y equals mx plus b, and regardless of what form it is in, the first thing we really want to do is find our slope and find a point. That point could be the y-intercept. It could be any other point, but we want to find our slope, find our point. Remember that our slope is our rise over our run, and start at any ordered pair, and then we can move up and to the right or down and to the right, depending on if our slope is positive or negative, to graph the next point, and the next point, make sure that our graph has arrows on the ends, and we really want it to take up the entire grid because we don't exactly know where the quadratic is going to cross that line. So first, graph your line, then graph your quadratic, and here's a little reminder on how to graph our quadratic. Remember to first find the axis of symmetry, x equals the opposite of b over 2a. You can plug that in to find the vertex and graph your vertex. And then you can make a table to find 2 more x values and y values for your quadratic and reflect those over to the other side, and then connect the dots to graph. You need to make sure that your quadratic keeps going until it intersects the line, because the solutions are those intersection points. So you're going to graph the line, you're going to graph the quadratic, and then you're going to identify what the ordered pairs are where they intersect. That's really what we're going to be doing in this video. So we're just going to look at 2 quick examples here and then wrap up this video. So again, the goal here, graph the line, then graph the quadratic, then identify the points, if any, where they intersect. So let's start with our line here. Y equals x plus 3. So I know this is the line because there's no squared term. The slope is the number in front of my x, which is 1, which I'm going to write as 1 over 1 to remind me that I'm going up 1 and right 1 each time I move. I need any point. If I plug in 0, I get 3, or I can identify that the b value is 3, so my y-intercept is 3. So I'm going to plot my point first, 0, 3. Then I'm going to go up 1 and right 1 and put another point, up 1 and right 1 and put another point, until I've gone off the grid. And then, since I don't know where this is going to cross, I'm going to actually also go down 1 and left 1 and go off the grid to the left. Then I'm going to connect and make sure I have arrows on the ends. All right, now I'm going to graph the quadratic. So the first thing I need to do is find the axis of symmetry. So x equals the opposite of b, which is -4 over 2 times 1. So this is going to be x equals -2 is my axis of symmetry. I'm going to draw a dotted line at x equals -2. I'm going to plug -2 in to find the vertex. So y equals -2 squared plus 4 times -2 plus 3. Y equals 4 minus 8 plus 3, which is -1. So my vertex is -2, -1. So now I'm going to make an xy table. The vertex is going to be in the middle of that table, -2, -1. I'm going to put points before and after. If I plug in -1, y equals -1 squared plus 4 times -1 plus 3. 1 minus 4 plus 3 is going to give me 0. So -1, 0, and -3, 0. And then if I plug in 0, I get 3, which I can reflect over. And I'm going to connect. And now I'm going to identify the 2 points where they cross. So it looks like they're crossing here and here. And my graph, again, on an iPad, not the easiest thing in the world. It looks like they're crossing at 0, 3 and -3, 0. But to confirm, I'm just going to plug those 2 points in. I can tell that 0, 3 is here. Well, yep, that works. 0, 3 is definitely on both of them. -3, 0 is here. If I plug in -3 for x here, I would get 0. So these are going to be my 2 solutions. What I hope you noticed, though, is that when I was doing that, even though I had exact numbers and I was taking my time, my graph still made it incredibly difficult to identify. This point doesn't look like it's on the axis, and it's not because I didn't take my time. It's because, well, number one, the iPad, doing notes on the iPad, but also just it's really hard to get exact, precise graphs. So one of the things I want you to think about is that there has to be another way to do this so that we can be more precise and positive about our answers. So what I want you to do really quickly is pause the video, look at number 5, and then go ahead and just graph this line. Identify the slope, identify the y-intercept, and graph the line. So our slope is 1, which means upright and 1 right. Our y-intercept, or a point on the graph, is 0, 1. So I'm going to graph the point 0, 1, and I'm going to move up and over 1. Once you have your points, you're going to connect your line with a straight edge. Then we're going to move on to our quadratic. So axis of symmetry, x equals the opposite of 2 over 2 times 1, which is going to be -1. X equals -1 is our axis of symmetry. If I plug -1 in, -1 squared plus 2 times -1 plus 1, 1 minus 2 plus 1 is going to give me 0. So our vertex is -1, 0, which is actually already a solution because that is a point on the other graph as well. But I'm going to create my table. I'm going to put negative 1, 0 in the middle of my table, and I'm going to identify some more points on here. If I plug in 0, I get 1. That looks like that's going to be my second solution since that's on the other graph as well. Reflect it over. If I plug in 1, I get 1 plus 2 plus 1, I get 4. And then I'm going to connect and identify my other solution, which was 0, 1. So on both of these examples, the quadratic and the line crossed twice, and we had 2 solutions. So actually, let's look at one more that is a different case. So here I have the line y equals negative 1/2 x minus 3, and the quadratic y equals x squared. So let's look at our line first. Our slope is negative 1/2, which means we're going to go down 1 and 2 to the right. Our y-intercept is 0, negative 3. Down 1, right 2. Up 1, left 2. And then we're going to connect. And then my quadratic, y equals x squared, the axis of symmetry, x equals 0 over 2 times 1, which is 0. So the axis of symmetry is my y-axis. If I plug in 0, I get 0. So my vertex is 0, 0. This is actually the parent function, so hopefully you don't need to make a table, but you could, negative 1, negative 2, 1, 2. If I plug in 1, I get 1 squared, which is 1. If I plug in 2, I get 2 squared, which is 4. So I can graph the point 1, 1, and negative 1, 1, and 2, 4, and negative 2, 4, and I can connect. And I'm not looking for where my quadratic crosses the x-axis, which is a little important to remember since we just spent so much time solving a quadratic. I'm looking for where the quadratic crosses the line, and that never happens. So what we would say is no real solution, or we would put the empty set, since it is not ever the case that these 2 functions intersect in the xy coordinate plane. So to recap this section, a nonlinear system is a system that involves at least 2 equations, and at least one of those equations is not a linear equation. What we're going to focus on, and what we focus on in this section, is a quadratic and a line. When that happens, a quadratic and a line can either never cross, as in that last example, which means they have no solution. They can cross exactly once, or they can cross twice. We talked about how to identify the solution when you're given a graph, just looking at where they intersect, and how to actually create a graph, graphing the line. We reviewed graphing a line, graphing the quadratic, and identifying the points where they cross. Now this idea can be extended. We could talk about what happens if we have a line in a circle, or what happens if we have a quadratic in a circle, but that really builds on concepts that we haven't learned up to this point in this course, but you will be looking at in future courses. What we're going to do in the next video is we're going to take some time to talk about how could we do this without graphing? How could we do this algebraically using substitution or elimination? So that's what you have to look forward to. Make sure you write down any questions, post them below, and I look forward to supporting you on this. Thanks for listening.